Okay. Well, we are all here learning more about probability and stochastic processes and random variables and all sorts of things. And I hope that in dealing with this stuff, you can see some real world applications, and it's going to affect your interpretation of phenomenon. I remember of having, how would you call it? It's kind of a paradigm identity. And I remember taking a course, first of all, in fields and waves. And I looked at transmission lines and I thought, wow, I saw transmission lines everywhere. And I remember toilet paper. Why does toilet paper tear at the roll? You know why? Because when you pull the toilet paper, it launches I shouldn't say toilet paper, I should say paper towels. Why do paper towels tear at the either end? They never tear in the middle, right? If you have a long reach for them, because you generate a wave down there and there's an impedance mismatch at the roll. And because you have that impedance mismatch at the roll, you have a break there because there's a greater amplitude. So I remember thinking about stuff like that. So I'm hoping that as you look at these random variables and stochastic processes, you can see the applications that are out there, hopefully in your own field, of research. So let's go on and let's begin to talk about the homework, which will be due next time that we meet. And I know you guys are busy, but too bad. I hate to say that, but I go ahead and do that. Okay, cars go by at a point. We reviewed these last time. Cars go by at a point on University Avenue at an average rate, et cetera, et cetera. No cars go by for 5 seconds. And then what's the probability that no cars go on after 6 seconds? And then there was the other one, a sequence of IID random variables. And I asked you to generate the mean, the autocorrelation, and autocovariance, and then ask if X is stationary and if X is Gaussian or close to Gaussian. We actually answered C, I think, in the class. So I think that you only have A and B to do. So does anybody have any questions on this?
There's the roulette question as well, right?
Yes, the roulette question. I'm sorry, I skipped that. A roulette wheel has 37 slots. So it's just generation of a confidence interval. This is stuff that you had way back probably when you took a course entitled something like Probability and Statistics for Engineers. And when you computed it, you probably had the tools, but you didn't know where they came from. Now you know where the tools came from. So hopefully this will put this in a new light and also give you a deja vu of your course of random variables and stochastic processes for engineers, or whatever the title was. Okay, thank you. Thank you. Any questions on these at all before we go on?
The last question is not for next Tuesday?
No, this is not for next Tuesday. This is for the next time. And I'm going to add to it, explain how you would estimate the autocorrelation of a stationary random process from an ensemble. We will talk about that next time, and that will be in the next batch of homework. I wanted to write that down while I could. Okay. Okay, well, hearing nothing then, let me go ahead and re-begin the lecture where we left last time, and that was on the idea of ergodic theorems. Okay, my pauses here is because I got to look for screens and all sorts of things as I click my way into a beautiful presentation. Okay, we're going to talk about the concept of ergodicity at this lecture. Ergodicity is a really interesting concept because the idea goes that many times you don't have an ensemble. Remember, we said we could generate the things like the ensemble average and even the probability density function and the second order probability density function also. If we had an ensemble of like-minded stochastic processes, right? And we could generate it. There was no assumptions of stationarity or anything else. Now, one of the problems is that many times in practice, you don't have availability to an ensemble. You don't have a bunch of different results. So this leads to the idea of ergodicity, wherein you only have a single waveform that you can look at. So this is what I just said. In many cases, an ensemble of random processes cannot be obtained. And if the parameters of a random process can be found from a single observation of the process is said to be ergodic. So in other words, if you can generate the mean of a stochastic process by looking at one instantiation of it, that process is said to be ergodic. And you have different types of ergodicity. For example, you want to compute the mean of a stochastic process. If you can compute the mean of a stochastic process with one observation, one long observation, that's referred to as mean ergodic. And there is also distribution ergodic. For example, if you want to estimate the distribution, the probability distribution of either a joint or a, or if you will, a joint or even a higher dimensional probability density function from a single realization, that's referred to as distribution ergodic. And these are different types of ergodicity. So with that, let me kind of explain here. Let's see. Yeah, let me explain here what at least one interpretation that is going on. Mean ergodicity. Okay, there we go. We do have a thing. By the way, I found out that my cursor is not available on the video, so I'm not going to try to point with my cursors without doing a check here. Okay, I don't know what this is. This is a long stochastic process as a function of t. Here's one way to think about ergodicity that I think is valuable. Suppose you had a stochastic process here. And this stochastic process went on forever and ever and ever. There are some situations where you could literally make this single observation into an ensemble. In other words, you could take this part of the stochastic process, and I won't try to generate it exactly. You would take this part of the stochastic process and make it into x, say x sub 1 of t. And then you could come out here a little bit further and you could take this part of the stochastic process. And remember, this is stationarity. So stationarity doesn't consider where the origin is at. You can have this result anywhere you want to. And you can take this portion of the stochastic process and you can get x sub 2 of t. This is just a thought process to kind of connect this idea of ergodicity onto the idea of performing statistics with ensemble averages. And then you can take this one, of course, and you can make it into x3. So you see, if you have a sufficiently long result, if you have a sufficiently long instantiation of the stochastic process, do you see how you can make these ensembles from it? But there's some assumptions here. And what are the assumptions? Well, one of the assumptions is that this part of the stochastic process has nothing to do with this part of the stochastic process. Does that make sense? That they have nothing to do with each other. Otherwise, you don't have independent instantiations in your ensemble. So in some way, we must go far enough out in order to assure that this part of the stochastic process has nothing to do with this part of the stochastic process. So in a way, we can say that this part of the stochastic process is either uncorrelated or independent from this stochastic process. We're talking in heuristics now, but I think you can see that we have to have this relationship that this part of the stochastic process has nothing to do with this one. Likewise, this part of the stochastic process, which we use down here for x3, can have nothing to do with this first part of the stochastic process or the second part. Does that make sense? So this at least intuitively ties together, in my mind, the idea of generating statistics from a single instantiation and then from a number of instantiations. In other words, an ensemble where we can do an ensemble average. So here we could go down, and if you recall, we could do things like generate this point and we could get the mean at this point, et cetera. Now, again, the assumption is, number one, is that it's stationary. it has to be stationary in order to say that this part of the signal looks exactly like this part of the signal. And this part of the signal looks exactly like this part of the signal. They're not exact matches, but they match statistically. So maybe statistically in the wide sense. Again, we're just talking in generalities here. So that's one thing. And the other thing is that there has to be a finite correlation length. What do we mean by a finite correlation length? That is the length where you have a stochastic process. You have a stochastic process, and you come out here, and here's x of t. And you have the value here. This is the value at the origin. You have to come out here, and you have to say, okay, this part of the stochastic process, which we'll call x hat of t, for example, this part of the stochastic process has to be totally uncorrelated with this part of the stochastic process. It has nothing to do with it. And you will hear in the literature and in different places the concept of correlation length. Has anybody taken a class in optics at all? No. Anybody know how to make holograms? No. Does anybody know that if you interfere two converging laser beams, you get constructive and destructive interference from it? Have you heard of that? Okay, well, there goes those examples. Okay. It turns out lasers, for example, have a coherence length. And if you make the beam too long, that one part of the beam has nothing to do with the other part of the beam, and you can't make holograms with it. So anyway, I won't go into that example since we don't have a lot of resonance in that area. So anyway, this is the idea of ergodicity, at least my intuitive idea. Now we're going to abandon this idea, and we're just going to look at what is needed for a single instantiation of ergodicity. And we're first of all going to look at mean ergodicity. Now, mean ergodicity means that we can compute or estimate the mean from a single instantiation of the stochastic process. And let's look at the stochastic process. Here we have a stochastic process, and here is mean ergodicity. Now, this was from a random number generator. I just used a random number generator to generate numbers that were random between 0 and 1. Does that make sense? Now, if I did this, what is the mean of the stochastic process?
0.5.
Yeah, it'd be 0.5, right?
Yep.
Because each random variable is halfway between 0 and 1. So the mean here would be 0.5. This would be the x sub bar. And again, we're going to assume that we know it's stationary. Now, suppose that we knew that it was stationary, yet we didn't have the ability to determine a priori what that mean was. One way to do this is to go out here and build a false boundary. And we'll assume this is all ice, okay? And what we're going to do is we're going to melt the ice, and we're going to see what level the ice comes to. Does that make sense? So we melt the ice, and I don't know, we get something like 0.511 or something like that. If we melted the ice in this case, we would come to a value of say 0.53. I don't know, some sort of value. Correct? And so it would be the mean of this from one realization. Now, what happens, do you think, to our estimate of this mean as this boundary shifts to the right more and more? It's going to become more and more accurate, isn't it? It's going to become more and more accurate as we melt more and more ice. It's kind of like an appeal to the law of large numbers. It's going to become more and more, trying to complete a sentence, more and more close, but that doesn't make it in terms of English. It's going to become closer and closer to the actual mean. So that's what we can do. We can talk about mean ergodic samples. And one of these is, interestingly, the battery factory. I'll give you an example of something which is not mean ergodic, but which is stationary. Something you can use an ensemble average on, but you can't grab the result from a single instantiation. So let me unshare and go to the whiteboard and illustrate that. We have a battery factory, and there we generate batteries. And these batteries are what? I don't know. What's a AA battery? What's the voltage on a AA battery?
1.5.
1.5, okay. So we take out one battery and it's 1.55. So that's the voltage across one battery as a function of time. These are very boring stochastic processes, by the way, as you see, but they're really going to illustrate the point. We have another one, and this other one that comes out is going to be 1.49. So this is x1 of t. This is going to be x2 of t, and that's going to be 1.54. And that's going to be a constant as a function of time. This is our x sub 2 of t. And then we're going to keep on going. We're going to do a whole bunch of different batteries. And we're going to come down here, x sub n of t. N is maybe a big number, and maybe that's 1.48, for example, 1.48 volts. Does that make a sense? These, again, are very, very boring stochastic processes. But I chose them for a specific reason. I chose them because of the simplicity of the definition. Now here, we can choose any point. Now, if we choose this point and do an ensemble average down this point, will we get the mean of the stochastic process at this point? Say t is equal to 4. If we do this average at 4, will it approximately be equal to the mean? In other words, the mean of all of the voltages of the battery coming out of the battery factory. Yeah, it will, won't it? Correct? In a similar fashion, we could go down here and we could make a histogram of all these values, and we could get a histogram of the values around, let's see, 1.5. And we could get a histogram along these values. And this histogram would be an empirical estimation of the probability density function. Do you see how we could do that using these values? So this is well and good. This is a nice stationary stochastic process. You can use an ensemble in order to get any of the statistics that you want. Let's apply the concept of ergodicity. What is ergodicity? Ergodicity is identification of the statistics of the underlying process with one observation. So let's take a single observation. Let's take this x sub 2. This x sub 2 has a value of what? 1.54. And that kind of goes on forever. Now, here's the question to you. And the answer should be kind of obvious. Will we, in the limit, get the average of the values of the batteries coming out of the battery factory? Absolutely not, right? We just have this single observation, which is 1.54. So there's no way that we can get the mean out of this. So this is an example. The battery factory example is probably a simple degenerate example of a stochastic process that is nice and stationary, number one, but number two is not ergodic in the mean. We cannot grab the mean at one observation of the stochastic process. Does that make sense? So all of that stuff that I drew before, where you took one part and you did another part, you took one part of the stochastic process, took another part of the stochastic process, and you kind of lined them up in an ensemble. Yeah, that worked there, but does it work here? If we took this part of the stochastic process, say from here to here, and we took this part of the stochastic process and we tried to make an ensemble from here to here, one of the things that was required is that this part of the stochastic process had to be totally uncorrelated with this part of the stochastic process, right? Are they uncorrelated? No, they're correlated to the maximum degree that they can be correlated, right? So one does have something to do with the other one. So we cannot do an ensemble from the battery factory. And you can see from the idea of ergodicity, we can also not not generate the mean from a single observation. We can't melt down the ice, if you will, and see where the ice melts down in order to get the overall mean of the stochastic process. So that's well and good. So therefore, our conclusion is that there's stationary stochastic processes that are ergodic. We have yet to explore ergodicity, number one. But number two, there's some stationary processes that are not ergodic. In other words, you cannot generate the statistics after one observation. So let's go back to the slides and see what trouble we can get into. So what I just did is I did a little sidebar here in that we have situations which are not mean ergodic, and that includes the battery factory example that I just gave you. Many examples are mean ergodic. If you take the hum in the background of a signal that where some antenna is picking up the 60 cycles, yeah, that turns out to be ergodic. If you talk about background noise or the noise floor in a microwave measurement, yeah, that's going to be mean ergodic. But there are examples which are not mean ergodic. So let's explore this a little bit more. In order to estimate the mean ergodicity, what do we have to do? Well, here's the obvious result. Say that we have an observation up to time t. We have the stochastic process, and we would like to estimate the mean by melting the water. What is the mean here? By the way, we're assuming that ice doesn't contract or expand here, if you will. Okay, it's just an illustration. If we were to melt the water, we would get some sort of estimate of the mean here, correct? So what is that equal to? That's the integral from 0 to t divided by t, right? That's the water level. So it's the integral from 0 to t divided by t. So this is exactly what it is. So we are going to assume here that the stochastic process goes from minus t up to t. And so here's the stochastic process. So we're going to assume it's stationary. By the way, you notice that kind of implicit in the idea of stationarity is that the signal has gone on forever, right? Because the statistics have to be invariant to time shift. So a stationary stochastic process, at least in theory, has to have originated at minus infinity in order for the statistics here to be equal to the statistics here. Anyway, that's just a side. But we have an x of t here. And if we are to estimate the mean over this interval from minus t to t, we would integrate over this interval. Here we have the idea of negative ice, of course. We would integrate this and then divide by 1 over 2t, which is the estimate, which is, I'm sorry, the interval between the values, 2t. And we use as this estimate a bracket. We haven't yet established what this value is, but you'll notice that whatever this is, it's not an average anymore, but it is a statistic, right? If x of t is a random variable, then this time average is going to be a statistic. And what we're hoping is that t gets really, really, really big, that the statistic is going to approach the mean of the stochastic process, of the stationary stochastic process. So let's take a look at this. If x of t is wide sense stationary, the expected value is the expected value. This is no time average, but one of the things that we would like is that the expected value of this statistic is equal to the mean of the stochastic process. Do you remember in days of old, we talked about the average and we showed that the expected value of the average was the mean? Well, let's hope that the expected value of the average is the mean, because that's what we're trying to estimate. The expected value of the average was the mean before. Here we have the expected value of the time average. We're hoping that that's the mean. And indeed, it is the mean, because if x of t is stationary, the expected value of the time average is equal to this. And taking the expected value on the inside, the expected value of x of t here just becomes an x bar, right? since it's a constant under the assumption of wide sense stationarity. And then we're just left with what? 1 over 2 x bar over 2t times the integral from minus t to t of dt. And of course, the t's cancel each other out, and we have x bar. So indeed, we have that the expected value of the time average is equal to the mean. But that isn't enough, isn't it? With the law of large numbers, we would like the variance of this statistic, the variance of this statistic here. We would like the variance of this statistic to go to 0 as t goes bigger, right? Because if the variance of this time average goes to 0, we're kind of assured, at least in the sense of the law of large numbers, that the time average converges to the mean of the stochastic process. So 2 criteria would like the time average, its expected value, to be equal to the mean of the stochastic process. It is. We just showed it. We would also like the variance of the time average to go to 0 asymptotically as t gets bigger and bigger and bigger. And in that sense, we are going to have a law of large numbers working for us, and we are going to be assured that we can measure the time average. We can estimate the mean of the stochastic process sufficiently with the time average. Okay, good so far. So the next thing we have to do is to compute the variance of this statistic, right? Because we would like the variance of this time average, we would like the variance of this time average to go to 0. So let's spend some time to compute the variance of this random process. Well, first of all, we know that the expected value is equal to x bar. We just proved that in the previous slide. We'd also like the variance of x of t to go to 0 as t goes to infinity. And if this is true, then x of t is mean ergodic, which means that we can estimate the mean with one realization of the stochastic process. Does this mean that we can compute the autocorrelation with that stochastic process? No. If something is mean ergodic, it doesn't mean that it's autocorrelation ergodic. It doesn't mean that it's distribution ergodic. Those are different proofs. So you can see ergodicity is pretty complexicated. If I can coin a word, it's a complexicated way of thinking about things. And we're going to get some interesting results here just from the mean, which is the simplest of the cases. So onward. Here it is. Okay, here we go. Let's jump through the mathematics. The variance of x of t, this is the definition of the variance. So we could put little is equal to by definition here. It's equal to the expected value of the stochastic process time average minus the mean, and we know the mean is equal to x bar. We're going to expand this out into, this is squared, of course, and we're going to expand this out into 2 different integrals. The first one is the expected value of x of t minus x bar. The second one is the same thing, except we've changed the variables of integration here. The reason we changed the variables of integration is because eventually we'd like to fold these out. We'd like to shuffle, if you will, these integrals together to come up with a single integral. And so we got to make sure that the dummy integral here is different than the dummy integral here. So if we do that and we put both of these integrations on the outside, we get this result. We get the integration from minus t to t from the first integral, the integration from minus t to t of the second integral, plus we get the 1 over 2t squared, which is the 1 over 4t squared. And then we get this expression, this expected value of x of t minus x bar, x of tau minus x bar. Well, here's the cool part. If you remember, what is that equal to? That's equal to, drum roll, the autocovariance. That's equal to the autocovariance. Therefore, if the stochastic process has an autocovariance where this goes to 0 as t becomes larger and larger, capital T becomes larger and larger, then we have a mean ergodic system. So that is the criterion for having mean ergodicity. Now, let's see if we can simplify this integral a little bit. If we can simplify this integral a little bit, we get the following. I'm going to simply repeat the equation that we had at the bottom of the last bar. And then what I'm going to do is I'm going to take this minus t over t, and I'm going to put a rectangular function here. This rectangle function just goes from minus t to t, and it has a value of 1. So if this is a function of t, this function here is going to be pi of t over 2t. Why do I want to do that? I want to take the integration from the finite interval here, and I want to make them infinite. I can make them infinite if I chop off the integration using these rectangle functions here. So that's what I've done. I've chopped off the integration by using these rectangle functions here. And this allows us to get a little bit more simplification. So this is the definition of the rectangle function, detailed if you're interested in it. But I would just think that this would suffice, this picture of the rectangle function. Okay, do a little bit more. Okay, the variance then is equal to 1 over 4t squared, and I ran out of room here, so this is times. This is not 2 lines. This is 1 line continued on the next line, is equal to this result. That's on the previous stage. And now what I want to do is see if I can get rid of one of the variables. And what I'm going to do is I'm going to let c is equal to t minus tau in my integration. Why would I ever want to do that? Well, it's because it takes this t minus tau and it makes it into a single variable. Right now it's a function of 2 variables. But we haven't taken into account the assumption that our signal is wide sense stationary. So we should be able to just make this substitution and put it in here, turn the crank and see what happens, and something nice happens. It takes a little while, but we get this result, we get blah, 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 blah. But we get down here, and it turns out if we make that variable substitution, we get the autocovariance function times this, and it's a convolution. It's a convolution between 2 rectangle functions. It's a convolution between 2 rectangle functions. And if you remember, the convolution between 2 rectangle functions is what? Is kind of something which we call a triangle function. And the triangle function goes out here to minus 4t. Over here, it goes over to 4t. And it has a value here of 1. So this is the definition of the triangle function that I have used here. So again, just turning the crank after this variable substitution, a convolution just pops out of the air. And out of this convolution, we can perform this convolution offline, because this is true no matter what the autocovariance is. We can do this convolution offline and generate this triangle function. So equivalently, if this thing goes to 0 as t goes to infinity, then we have a what? We have a mean ergodic stochastic process. Because if this goes to 0 as t goes to infinity, we're assured that the variance of t, don't forget what we're computing. We're computing the variance of t as t gets bigger and bigger, and we don't want to get lost in the weeds here of all the computation. But we're hoping that this variance goes to 0 as the observation becomes larger and larger and larger. And indeed, that's what we get here. Okay. We get a simplification and we get a triangle function. We doing okay? And here's the definition of the triangle function on the bottom right, if you want to get interested in the triangle function specifically. Okay, let's continue. Here's what we just showed. We showed that if this goes to 0 as t goes to infinity, then the stochastic process under examination is mean ergodic. Notice this ergodicity is not a simple problem, is it? You got to jump through a lot of integral calculus here in order to do that. So therefore, a wide sense stationary random process is mean ergodic if, and here it is in a big bold block with green highlighting, if the limit of this thing goes to 0 as t goes to infinity. So let's talk about this a little bit, and let's talk about let's talk about an instantiation. I mentioned parenthetically here that the decimal criteria holds for discrete time stochastic processes. All of these things, I hope you can make the jump from continuous time to discrete time, because it's not that big of a jump, hopefully, at this point in your career. Okay, let's take a look at the telegraph signal. Do you remember the telegraph signal? Now, we showed, I don't know if we showed this, but it turns out that this is the autocovariance. This is the autocovariance of the telegraph signal. And if we remember what the telegraph signal was, okay, let me remind you what the telegraph signal was down here on the bottom. A telegraph signal is when you do random Poisson points. You do random Poisson points on a timeline, and then every time you hit a Poisson point, you switch from, let's see, I think we just did the binary. So I think it goes from, yeah. It goes from 0 to 1, and then every time it hits a Poisson point, it either toggles back to 1 or back to 0, okay? So this would be an example of a random telegraph signal. Do you recall that from the talk about different classes of stationarity? Okay, well, let's see if it's mean ergodic. By the way, do you think that looking at this would be mean ergodic? Do you think if we took a big enough instantiation of this and melted the ice, do you think we would get a good estimate of the mean? What do you think the mean is here, by the way? It's kind of obvious, correct? The mean is obviously 1/2. You think if we melted the ice, we would get 1/2 if we took the average here? Well, here's the criterion. The criterion is that 1/2t times this integral of the autocovariance, which we're given here, times this triangle function goes to 0. Well, it turns out you can simplify this, and I won't go through the details, but you can simplify this using the autocovariance up here, and then this triangle function, writing this as this, and then you can evaluate this integral. And let's say I'm saying that the second part goes to 0. Why does the second part go to 0? That is not obvious to me right now. But let's just assume that the calculus going from here to here, not the calculus, but the algebra going from here to here is true. And anyway, this turns out to be 1/t, integral from 0 to 2t of this exponential. And I've made a count of the fact that this is an even function. So instead of integrating from -infinity to infinity, I can integrate on one side and just double the result. So it's this, and we have an exponential here. This is an e to the -2 lambda t. Lambda tau is a function of tau. And then we have a 1/t here. We have a 1/t there. Now, this goes out from 0 to 2t. And here's the question. As t goes to infinity, this goes this way, right? As t goes to infinity, this upper bound goes to infinity. But the amplitude, this 1/t term tanks. And so eventually what you get is you get an exponential with just nothing here, and it just kind of goes on forever. And eventually this 1 over t term is going to dominate in the integration, and it's going to go to 0. Isn't that cool? So therefore, our intuition is satisfied that the telegraph signal is mean ergodic, and that therefore we can look at one instantiation of the telegraph problem, a telegraph stochastic process, and we can look at one realization and we can estimate the mean of that stochastic process. It is mean ergodic. Notice again, it is not ergodic. Ergodic is too big of a word. We haven't proven that it's variance ergodic, distribution ergodic, or correlation ergodic, or anything else. We've just shown that we can estimate the mean from a single realization. We haven't shown that we can estimate the autocorrelation from a single observation. Just the mean. So you can see this gets pretty involved. So therefore we can conclude that it is ergodic. Let's look at the battery factory. We said that intuitively the battery factory was not mean ergodic. Let's see if this formula bears us out. If we have a battery factory and we just have a single value here, we just have a single value representing all of the results, then it turns out that the mean of the batteries is hopefully going to be 1.5, right? And what's the variance going to be? The variance is going to be whatever it's going to be. But that variance is going to be the same here as it is here, as it is here, because each one of the batteries is just a constant, right? So the variance at every point is going to be exactly the same. And when you have a result like that, it turns out that your autocovariance is nothing more than the variance of the stochastic process, which is a constant with respect to time. So that is the autocovariance. So let's take a look at the math behind it. Here is the general criteria. This is the general criteria. And here is the here is the instantiation here. It turns out we can take the variance of x, factor it outside, and we get this integral. And this integral is not good, man. It isn't good. It says that we have from minus t to t, if I have this right, we have something with a height of 1 over t. And if that's the case, what is the area here? Always should be able to do a little bit of geometry. Come on, the area of a triangle.
1/2 base times height.
1/2 base times height, which is what?
That'd be 1 here.
It'd be 1. This has an area of 1. Come on, guys. You can take this part of the triangle, and then you can take this part of the triangle and put it over here. We're just trying to compute the area, right? If you take this part of the triangle and put it over here, you get the idea? This is simple geometry in your head sort of stuff. You get something, you get a rectangle of length t and a height of 1 over t. So this is always going to be equal to 1, correct? So therefore, this integral is always equal to 1. Not too exciting, right? That integral is always equal to 1. And in that case, this criterion that we have turns out to be the variance of x, because that's the thing that's carried along here, the variance of x, and that's not equal to 0. Remember, we have to have this be equal to 0, this top equation equal to 0 as t goes asymptotically to infinity. But here, as we have capital T go asymptotically to infinity, we just get the variance of x. It does not go to 0. So therefore, we cannot trust the battery factory to be a stochastic process that is mean ergodic. And that, again, is consistent with our intuition. But the kind of the nice thing here is that the mathematics proves our intuition that the battery factory is not mean ergodic. Okay, onward. Let's look at what would happen if we wanted to do autocorrelation ergodic. In other words, can we look at one instantiation of the stochastic process and determine whether it is autocorrelation ergodic? We can get autocorrelation ergodicity from an ensemble average. Can we do it with a stochastic process? And the answer is not always. We have to have a criterion, just like we did before with the mean. And what is that criterion? Well, for large T, we can approximate the variance by this result, right? This is the time average of the stochastic process times x of t minus tau. And then we have to do this for all values of tau. But let's look at it for just one value of tau. We're computing the autocorrelation at a single point. And so the question is, can we evaluate this? Now, believe it or not, we can use the same exact mathematics that we did before and think about this as the y of t. And we're seeing if y of t, and we can subscript this with a tau if you like, but we're saying that is the time average of y of t for a given tau, is that mean ergodic, right? So we've done the work already. It's just kind of interpreting this new thing as a new stochastic process, which we're going to call y of t. And then we're going to ask ourselves, is y of t mean ergodic? If that is true, then the autocorrelation is, that the stochastic process is autocorrelation ergodic. Okay, so we define for fixed tau. We're only evaluating this autocorrelation for a single value of tau. If we do this, we get y sub tau of t, that's our new stochastic process, and then x of t is correlation ergodic, and when y sub tau of t is mean ergodic for all tau. So this is all well and good. So we can apply what we did before to figure out if this autocorrelation ergodicity applies to the stochastic process. Unfortunately, we get something which is interesting. We must get this result, the expected value of x, y of t times this. This turns out to be the autocovariance. Remember, in the mean ergodicity, we had the autocovariance. So now we need the autocovariance of x sub tau. Well, here's the problem. X of tau is equal to, or x sub t is equal to this times this, and y of t is equal to this times this. Here's the interesting problem. This is a fourth order statistic. Therefore, we've only been looking at, I shouldn't say therefore, we've only been looking at to date second order statistics. We've been looking at the mean and the autocorrelation. We've been looking at 1 point, and then we've been looking at 2 points at a time for different separations of the points. And that got us to the idea of wide sense stationarity. In order to do the autocorrelation ergodicity, you have to consider the correlation between 4 different points on the stochastic process. You have to evaluate the autocorrelation of this point, of this point, of this point, and of this point. So it takes fourth order statistics. And that's something I'd prefer not to get into in this course, but you can see it becomes complicated very quickly, right? If we're to do autocorrelation ergodicity. Nevertheless, we should be able to intuitively do autocorrelation ergodicity for many interesting cases. We'll find out that you can always do this, for example, for a Gaussian stochastic process. And we will address that shortly. So this is the establishment of correlation ergodicity requiring fourth order moments of x of t, and this is more than wide sense stationarity. So it isn't sufficient for the process to be wide sense stationary. You have to have the fourth order statistics behave well in order to do autocorrelation ergodicity. So you can see the concept of ergodicity is a problem that we need to, pay close attention to. Any questions on that? I think that that's a fascinating result. I hope that you found it fascinating. Okay, I'm going to have to set up use a little bit of time to do my results here, to set up the screens that I want you to see. Okay. The next question we are going to address is analysis and processing of random or stochastic signals. Again, random signals, stochastic signals, same thing. It depends on how much you want to impress your audience. If you want to impress your audience, use the idea of stochastic instead of random. So here's a question we're going to ask here. Suppose that you take, and I'm going to give you an advertisement of what happens here, which is really fascinating. Suppose you take a stochastic signal and you place it into a filter with an impulse response of h of t. In other words, this is a linear time invariant system. So I am going to draw on your previous experience with linear time invariant systems. And you get a corresponding output, which is y of t. We're going to assume that h of t is deterministic. It's deterministic, so therefore there's nothing random about it. But if you know the statistics of x of t, can you tell me what the statistics of y of t are going to be? And we'll find out, and this is one of the reasons engineers are primarily interested in second order statistics, at least in the beginning, for rudimentary sort of stochastic processes, that if you know the hx bar here, and you know the autocorrelation of this function, we're assuming that they're wide sense stationary, then you can determine the mean of this output and the autocorrelation of the output. Now, that should not be apparent how you can do that, but that's where we're going to go in this portion of the lecture. So when we filter a stochastic process, say we run it through a low pass filter or a band pass filter or something like that, and we know the statistics, the first and second order statistics of the stochastic process of the input, and we are assuming that it's stationary in the wide sense, the sloppy sense, we can compute the statistics of the output and of the correlation of the output, the first and second order statistics of the output. And that is kind of cool. So let's take a look at this and start to think about it. First thing we're going to think about is something called the power spectral density. Now, this is going to blow your mind, and we could spend some time justifying it, but here's where I go to my story about Adolf Lohmann, which I shared in my multidimensional class. How many were in my multidimensional class? Okay, 2, 3. Okay, so only Matthew was not there. Okay, I met this famous guy, Adolf Lohmann. He invented the computer-generated hologram. And I was starstruck, and I got the chance to meet with him and talk to him one-to-one. And I asked him where he got his inspiration from. And his response was, well, what was the response? Do any of you guys remember? I want to see if this stuck to you.
I remember it.
What is it, Glauco?
Whenever you don't know what to do, just do a Fourier transform.
That's right. If you don't know what to do, take the Fourier transform. So Fourier transforms are all over the place. We've seen that the Fourier transform of the probability density function was the characteristic function, right? Now we have this wide sense stationary one-dimensional autocorrelation function, R sub x. What happens if we take the Fourier transform of that? We get something which is called the power spectral density. And it's not obvious at all, if you've heard of the power spectral density, it's not obvious at all that this indeed should be the case, but in fact it is. What is this power spectral density? The power spectral density has two things in here. It has spectral. So that means that the density function is a function of frequency. So we have a function of frequency. So whatever it is frequency. It's a function of frequency. The other thing is it's a power density. What is a power density? Well, if you have charge density and you integrate over it, you get charge. If you have probability density and you integrate over it, you get probability. If you have power spectral density and you integrate over it, you get power. So this is a function which we will call S sub x, and this is pretty well uniform notation. The power spectral density is usually S, and it's the power spectral density. And if you integrate over it and any things, the area here, the area, whatever this area is, has units of watts, if you will. Or if you will, it has units of power. Okay. And this is frankly amazing. So again, taking the Fourier transform of a wide sense stationary stochastic process gives one the power spectral density. Again, spectral means it's a function of frequency. Power density means integration over this function gives you power. How many have heard of the power spectral density? Okay. So two of you have. So at least you have an intuitive insight into what's going on. Now, first of all, anytime you have a Fourier, by the way, I should mention that don't confuse this with the characteristic function. Characteristic function is when you take the Fourier transform of the probability density function. The power spectral density is when you take the Fourier transform of the autocorrelation. They're two different things. They're just the use of the Fourier transform in two different applications. One has to do with the autocorrelation of the stochastic process. The other one has to do with the probability density function. And they're distinct ideas here. So as is the case, anytime you have a Fourier transform, you have the inverse Fourier transform. So we can get the power spectral density from the autocorrelation, the one-dimensional autocorrelation. We should be able to get the one-dimensional autocorrelation back from the power spectral density by performing an inverse transform. So this is an inverse Fourier transform, if you will. And here is one interesting thing. If you look at this and you look at tau is equal to 0, if you look at this as tau is equal to 0, this thing goes to 0, right? And this thing goes to 0 here. I'm sorry, this doesn't go to 0, it goes to 1, doesn't it? The e to the j goes to 1. And we're left with an interesting observation that the area under the power spectral density is equal to R sub x of 0. Do you remember what the R sub x of 0 is? That's the second moment, which is the average power, which is a constant under the idea of wide sense stationarity. So this is very interesting. It's a power spectral density S sub x as a function of f. And if you integrate over it, you look at all this area here, you get the average power. So this is consistent with our idea that if we integrate over the density, we do get power. Okay, what does this say? Does this say, for example, if we integrate from here to here? And because of the weirdness of the Fourier transform, we also have to integrate over here of negative frequencies, the mirror image, if you will. If we integrate from here to here, do we get the power associated with that frequency band? And the answer is yes. That's exactly what the power spectral density function is. So once you're in the power spectral density, if you want to find out the power, if you want to find the whole power, integrate the entire power spectral density. If you want to find just the power in a frequency band, all you have to do is integrate over that frequency band, and that gives you the power in that frequency band. So that's kind of sweet. So you might have not had an intuitive idea of what the autocorrelation was, but you should have an intuitive idea of what the power spectral density is. At least that's my case. I understand the idea of correlation, but you know, the autocorrelation function. Yeah, okay, I kind of get it. It's how the two random variables are correlated. But the fact that this Fourier transform is the power spectral density gives me, as an engineer, something solid that I can grab onto intuitively. So it's the power spectral density, which is the Fourier transform of the autocorrelation. Now notice there is the assumption of wide sense stationarity here. You cannot have a power spectral density of a non-stationary stochastic process, because this Fourier transform assumes that the underlying stochastic process is wide sense stationary, and therefore the autocorrelation is just a function of a single variable. Here are some of the properties of the power spectral density. First of all, as we said, that the area of the power spectral density is equal to the average power in the stochastic process. Also, it turns out that it's even. It's even. This comes from the fact that you might remember this from Fourier transforms, that R sub x of tau is equal to R sub x of minus tau. It's an even function, but this is conjugated in the case where you have a stochastic process, and that this is a minus tau. I should have said this is a minus tau. And if you remember that any time that you had this sort of relationship, that it Fourier transformed back into a symmetric function on the other end. So that's one of the criteria for a power spectral density, and it comes from the structure of the autocorrelation function. S of x is real. Turns out that this does not grab onto the idea of imaginary power. And we know we have imaginary power when we have quality factors and things of that sort. This doesn't deal with this. We have a stochastic process. That stochastic process has a number of interesting properties, but everything is real, and it just, it doesn't matter. And we will prove this idea that it's real later on. The other thing is that it is non-negative. In other words, we do not allow for the chance of having negative power. If you have a stationary stochastic process, it has power associated with it. It has positive power, and you cannot get negative power from a stochastic process. Everything is positive power. Okay. Here's the proof of these criteria, and this is for real stochastic processes. S sub f is real and R sub x is even. Therefore, if we integrate from minus infinity to infinity, this, of course, is Euler's formula for what? E to the, I guess this is minus. This is Euler's formula for e to the minus j 2 pi f tau, right? You take this and expand it in Euler's formula. Now this is even. This is even. And this is odd. Right? That's odd. Now the integral of an even times an even function is equal to the integral of an even function. But an integral of an even times an odd function is equal to the integral of an odd function, which is equal to 0. In other words, an odd function is a function which looks like this, right? And so this part eats up this part, and the overall area is equal to 0. So therefore, with this expansion of the inverse transform, we can drop this sign. We don't need that anymore because that's an odd function. And we're just left with the integral of r sub x of tau times the cosine. Now, both of these are even, and the integral from minus infinity to infinity of an even function is equal to twice the integral from 0 to infinity of an even function, right? So therefore, we can just double this and integrate from over 1n from tau is equal to 0 to infinity. So this shows that S, the power spectral density, is real. How do we know it's real? It's real because there's nothing imaginary in here, right? There's nothing imaginary in there. So it turns out to be a nice real function. And here's the other thing, and I alluded to this before, that if we have a desire to know what the power is in a certain band of frequencies. So here's our power spectral density. And we want to find out the power between a lower band limit and an upper band limit. It's a power spectral density. We integrate over it, we get power. We integrate from here to here, that gives us the power in that frequency band. Because Fourier transforms are weird with symmetry, we also have to include this part. So the total power associated with this power spectral density is the area of here plus the area of here. But because of the evenness, it's just twice the area of here. So this is twice the area of the power spectral density, and that's the power in the band. Let's see if you can figure out what the origin value is here. What is this value? Right? So can you tell me what the value at the origin is from this equation? Somebody turn on their microphone. Are they going to be brave enough to talk?
This is just the value of the autocorrelation?
Yep. So this is the value at the origin. Okay. Let's see. I think we'll probably pick up here next time. Let me check the time. Okay, we're a little bit over time. So with that, let me ask if there's any questions about the results. And don't forget that the homework that I assigned that we went over is due next time. Okay, there are no questions. I've either been very clear or very unclear. We'll find out with the homework, I guess. Okay, we'll see you. And we have, who is missing here?
Theo.
Theo is missing. Okay, well, I'm sure he has a good reason. And he will have the opportunity of viewing this on YouTube. So that's good. Okay, guys, take care.